As per normal, all credit goes to these people, especially Dr. Sanchez. He made most of this content. So over here, we're going to move on to basically soon this portion over here, but we have to finish this up. We're almost there to shockwaves, but we need to finish this last portion up real quick. And let me just write the boundaries so I don't make a mistake. Okay, those are the boundaries. With that set, we can write as we want. So first thing we need to note is that obviously we need to write that HO equals CP over TO. That is our T indicator. Now, we already know what TO over T is actually from previous. We know that this is density O over density alpha minus O from one equation. And then we know PO divided by P is equal to alpha minus 1 over alpha. That is given to you by the state equation with constant, I believe it was isentropic, constant, what's that called? Entropy. Yes, beautiful entropy. The best thing, one of the best things. Anyways, but what's not given to you is the statement. Now, if I give you HO divided by H, and then I say that equals to CP TO, and this is CPT, then we know that equals to TO divided by T. That we can say is true. Now, what is T? Next, the question you're going to ask me, which let's move on from that for now. Let's not talk about that for now. Instead, let's talk about the other definition of HO divided by H. We know that HO is defined by H plus V squared divided by, I believe it was 2. What does this really mean? It really means that we can do this. H plus V squared divided by 2 divided by H, which equals 1 plus V squared over 2H. Okay, we got somewhere. From that, we can realize we can plug back in 1 plus V squared divided by 2 CPT. Now, I know that the recording is a little laggy, so I'm just going to wait a little bit for it to catch up. But hopefully it did. I think it did. All right. Okay, we got this now. We got the beautiful equation here. Now, the real question is, but I don't know what how you no, it would get you A, but it wouldn't get you that yield. Yes, it would be figured it out. It is A square equal, I believe it's gamma P over density, and it's gamma RGT. And then it says A equals square root. So when I have T, that must equal A squared divided by alpha RG. It's the only way this makes sense. And that would mean this equals, I believe, 1 divided by 2 CP, and then alpha, so alpha RG divided by A square, very square. So we have a Mach number here. We have a beautiful Mach number here. So this will give you 1 plus, no, but we want to simplify even more to that form. So I need to use RG. I believe that equals CP minus CV. Does that help me? No? Well, I mean, this is going to be divided by CP, right? Which gives you 1 minus CV over CP, which is 1 divided by alpha, right? And we have alpha on top, so we're going to do alpha, which will give you alpha minus 1. So we get alpha minus 1, parentheses, Mach square. Is that right? Oh, that's divided by 2, I missed, but is that right? Yeah, beautiful. All right, we move on. Let me just read this portion over here because it's still writing. I mean, we read the other one, right? Let me just make sure. So say let's also have a main property. Okay, yes, streamline properties, stagnant properties. Yeah, okay, we're good. If the flow is inviscid and steady, consequently, the relationship of 2.40 may be used to determine the dominant variables of all those as function of local Mach number. It is worth emphasizing that equation 240 also serves as a general definition of static property, independent of the nature of the flow. For example, even on steady viscous flow, one may use the last relationship 2.40 to evaluate the stagnant pressure in terms of the thermodynamics static pressure P and Mach number M at a given state, instant, and location. Given instant and location. In that case, however, the stagnant pressure is not conserved along the streamline passing through that point and is therefore a limited usefulness for flow analysis. Okay, fair enough. We're going to go to now shock. And this is going to be where we go and talk about expansive wave and so on and so forth. So let me make a bound here so I don't go off there. Okay, so I'm going to write mostly here for this one. Let me read this real quick. For a solution of the Euler equation to represent adequately a given large Reynolds number flow, we need to consider in general existence of discontinuous surface across which the fluid properties or their derivatives of finite jumps. Mach cones, for instance, represent an example of a weak discontinuity with jump in derivatives. Yes. Boundary layers and also vortex sheets and mixed layers are example of tangential discontinuity. We shall focus below on the analysis of normal discontinuities, showing that they are always compressive waves, also called shock waves, with the specific result given below for jump condition plus normal and oblique shock. Conversely, expansive waves cannot be discontinuities. Rather, they are continuous isentropic waves to be analyzed below. In a specific case of a steady flow around a sharp corner is called frontal mirrors. Oh yeah, right. Very yeah. I think this is shown in 2.1a, I believe. Jump conditions across the specific surface to determine the condition that relates to the different flow property that exists in the side of a given discontinuous surface. We shall apply the conservation equation to an infinitesimally small control volume shown in figure 2.1 as it can be figure 2.1. Okay. 2.1, what's 2.1 theorem? But I don't remember what's called, so we're gonna have to like remember here. So it's gonna be integral dv, I believe. So let me just integrate this by dv real quick. And then that is, I believe, I got this, man. I got this. It's integral d integral dt. I don't really know why anyone would use this form, but I haven't seen a use for it yet, which is bad. So I think maybe this is the day that I get a use for it. Um, did I do this right? It's the question. Um, I don't think I did this right, but uh, I think something's wrong here. No, I did it right. Okay, fair enough. So, so this is a form, and from this form you can get, I believe, integral, and I think he still uses volume here, right? But you can move the derivative outwards and do a dv because this is a spatial unit and this is a time unit. And then we have to use a property of a surface, which is, I believe, they denote it by a summation or s. It doesn't matter which one you use. Um, I think I think I'm wrong about this. I think you just leave it like that. But then you do, I believe, you get rid of a something here and do a ds over here. And then you do v dot n with the density. Yes. I'm pretty sure that's right. Yes, I'm right. Thank God. Yes, okay. Yeah, it took a while. There we go. And then we have a QED, so we just do this. Okay, so from this, what can we do here is the next question. So we have to now look over here and bring this in over here. Now let's analyze this a little bit. So what we have here is this is our area, and so d tau is equal to ds. I did not realize he used he used d tau. It doesn't matter. It does matter for me. It'll confuse the hell out of me if I don't use the same notation. Um, what did he? Yeah. Okay. And what did he use for the one? Summation and C. Oh, okay, C, use C, because that's what he uses. And then d omega equals 0. Now, I believe the secret here is that notice that the time variable is nothing. I believe that's the secret. So you move this away, right? It's a tiny element, so we can denote this as the same thing. So this n and over here, this n is the same, right? So what that means is that we have, I believe it is a velocity and a density, right? And that's it. I don't think I'm missing anything, am I? I might be missing something. I don't remember. But this looks like it is exactly. And then they get this. Yeah. Yeah. I think that's it. They just integrate those things and we get their final version. Am I incorrect about something? I probably am. Probably made a mistake somewhere. What is M? M is defined by density and velocity. Now we're integrating this, so integrating all that. Yeah, we should be good. I think that is all. And obviously the density over here and density over here is different. And then the velocity over there. So yeah, that's how you get density 1, v1 equal plus, is it equal? Equal, yes. Equal density 2, v2. Because this integral is saying density 1, v1 minus density 2, v2 equals 0. Because you can remove an integral and get that form. That's the start of shock waves. Yeah. Okay.